Hello. This is these are groups 4 and 5, right?
Yes.
Yep.
Yes. Now, just a moment. Not this one. Oh, just a moment. People, on the second conference, do you see the lecture 3 types of relations screen?
No, we only see your webcam.
You see only me. This
The first and the fifth group.
Just a moment. Now, people from group number 4 and 5, do you see this screen? Types of relations, equivalence.
Yes.
You do. Because yes, don't hesitate to say it. Okay, now people in the groups 1, 2, and 3. Do you see the screen? On the screen, text, yes. Lecture 3 types of relations. Yes, now it's okay. Finally, thank you. Well, good afternoon, people. It's so kind of you to join me exactly on time. And, well, we finished discussion of binary Boolean functions. That's why I want to resume the lecture that we dropped before this jump to Boolean functions. I want to finish. It will be done quickly. But I hope also that you registered your attendance. Did you? If you did not, if you have not registered, please do it now. Also, I remind you that after this lecture, there will be at 1:10 a consultation. Those who want may join from any group, but do it please on the conference number one. Okay, types of relations. Well, people, are you ready to start?
Yeah.
So first of all, but as far as I remember, we discussed something of it. I will just remind you that we started to talk about deep level properties of relations, and they are such. Reflexive. A relation is reflexive, a binary relation. A relation defined on 2 sets. And for simplicity, we said that, well, let it be just 2 sets the same. Cartesian product of A by A. So in this case, we can speak about reflexive property. A property is reflexive if for every x from A, an element is in relation alpha to itself for every. In this case, reflexive. I don't discuss examples, I just remind you. A binary relation is called anti-reflexive or anti-reflexive. American variant or anti-reflexive if for every element x from A, the element is not in this relation to itself, is not in relation to itself. Example, for example, A is less than B, A is the son of B, etc. A cannot be a son of itself, of himself or herself. If a son, then it is he of himself, etc. A relation alpha is symmetric if for every x and y, the fact that x is in relation alpha to y implies that y is also in the same relation to x. For example, y is a relative, x is a relative of y. If it is true, then y is a relative of x, and so on. So if this is true, then this must be true for a relation to be symmetric. And a binary relation alpha is called anti-symmetric if for every x and y, the fact that x is in relation alpha to y and y is in the same relation to x, it implies, it means that x and y are equal, actually the same element from A. If x and y it is equal to, they are equal, and both of them belong to A, then it is the same element. Examples. Number A is less or equal to number B. Okay. If A less than B, less or equal, and B is less or equal A, then A, it follows, of course, that A is equal to B. Or the same for including these sets, relation of inclusion of sets, and so on. A binary relation alpha is called transitive if for every x, y, and z from this element A, set A, the fact that if x is in relation to y and y is in the same relation to z, from here it must follow x is in relation to z, y must, if this relation alpha is transitive. If sometimes this is true but this is not, then it is not transitive, non-transitive, as it says here. For every x and y and z from A, if x in relation to y, y is in relation to z, here I crossed. It does not follow that x is in relation to z. So in relation x and z. Does not follow. Actually, it means sometimes it is true, sometimes it is not. Then it is not non-transitive. For example, to be a son, then here it is in normal situation. X and Z, X is the grandson of Z grandfather. Yes, but not just son. Okay, and we discussed equivalence, a relation that possess three properties: reflexive, symmetric, and transitive. If a relation is reflexive, symmetric, and transitive at the same time, then alpha, such a relation, is called equivalence. And examples of such real-life relations between objects here, for example, P. If X is a relative to Y, Well, first of all, X is a relative to itself, to himself or herself. Well, we said why, because you are the dearest, the closest person for yourself. A relative, a relative. We can assume. If X is a relative to Y is a relative to X. So it is symmetry. And if X is a relative to Y and Y is a relative to Z, then X is a relative to Z also. But we don't say son or mother, father, son. Just relative. To have the same weight, to study the same academic group. And here, just to see more clearly how we can detect these properties, we can just represent the relation by a square matrix. Here, values possible of X. Actually, these are elements of set A. Elements of the same A. Maybe people, if we talk about relative. And after that, person 1 is a relative to himself or herself. Yes, of course. Person 2, for the same reason. Person 3, for the same reason. The main diagonal is filled with unities. That's why it is reflexive. After that, 3 to 1. Yes, it is true. Person 3 is a relative to person 1. In this case, person 1 must be a relative to person 3 for this relation to be symmetrical and so to be transitive. Yes. And after that here, why transitivity? I mean symmetric, to be symmetric. Look, it is here degraded case of being symmetric. 1 is a relation to 1. The same 1 is a relation to 1. Actually, we can, formally speaking, it is symmetric. It is symmetric. It is symmetric, which is supported by these unities. And transitive. 3 to 1. 3 to 1, true. 1 to 3, true. For this relation to be transitive, then 3 to 3, 3 must be in the same relation to 3. Yes, we find this one. That's why. And also here, this also represents transitivity, this unity. 1 to 1. After that, this 1 to 1 again. And after that 1 to 1, the relative, it is here. So all 3 cases are represented by this unity. In that case, in the case here, 3 to 1, yes. 1 to 3, yes. And 3 to 3, yes. Normally, we need 3 unities in a certain configuration for the relation to be transitive, but it is enough. These unities on the main diagonal, they also support or represent the property of transitivity. Also here, this is equivalence for the same reason. Here 1 and 1 here 2 1 and 1 2, and after that 2 and 2 here. It is just, and even this case is represents the relation of equivalence, where we have only unities on the main diagonal. And we discussed this is reflexive, symmetric, and transitive, and everything here in this same unity. Same here and same here. And here, relations on the same set 1, 2, 3 defined, but which are not equivalences. Here, it is reflexive, it is symmetric, but not transitive. Why? We have 1, 2, this unity 1, 2. After that, 2 to 3 here. They are so these pairs in the relation, but for relation R to be transitive, 1 should be in relation R to 3, but from 1 to 3 and here 0, 0. That's why not transitive. 1, we found one case that contradicts the definition of the transitivity, and the whole relation becomes not equivalent. Same here, it is not reflexive and not transitive. And here, reflexive, not symmetric, and transitive, but not symmetric. Why? Unity here, but 1, 3 here, but no 3, 1 here. Okay. Also, the relation of equivalence is a formal substitute of such everyday notions as to be interchangeable, to be identical with or to, with A is identical with B or identical to B, to be indistinguishable from A is indistinguishable from B. Okay, if we have some objects of the same color, yes, they are indistinguishable. Okay. The relation of science begins with collecting objects to be researched. And after that, this object should be somehow classified within the same one class. Objects must be indistinguishable from a certain point of view. That's why the task is to find the relation of equivalence of these on these objects. The relation of equivalence is a formal substitute. Okay, this relation defines a feature, a property that enables to make a partition of a set A, into disjoint subsets. With each subset, elements are indistinct on the basis of that feature. So partition, I mentioned partition, but I want to give a definition. A partition is a system of a system S. It is a set of objects, and the objects are divided into subsets A sub 1, A sub 2, A sub 3, and subsets such that these subsets don't have common elements. Intersection of any pair of these subsets is an empty set. Okay, and the union of all subsets from here make the whole set. My God, a mistake. S Сейчас. Секундочку. Just a moment, let me think. Nope. It was right. Because here I said it is a system and they are subsets. And here, collection of subsets, and I denote it by S. But also elements that are obtained here, present here, they all belong to set A. Actually, this A sub 1 is an element of S, but is a subset of A. Now, the union of these subsets make the entire set A. Okay, and here I say I and J take values 1, 2, 3, K, and I is never equal to K. Here. Never equal to J. Such subsets of set A are called equivalent classes of the partition or classification on S. On S. Here. We classify elements of the set A. Of course, sorry. Some binary relation sigma can be put into correspondence with each partition of A. So we partition elements of A if it is assumed by definition. So relation delta sigma can be put into correspondence with partition if it is assumed by definition that X is relation delta sigma to Y if both elements belong to one element or one class. This relation is equivalence Y because 1 for all X, they belong to the same class. If X, for each X and Y, if they belong to one subset, from here it follows that Y and X also belong to one subset. So if it is a partition, if partitions, classes that satisfy these conditions, and for every X, Y, and Z, if element X and Y are in one of these subsets, and Y and Z are in the same subset, then from here it follows that X and Z are in the same subset. So if we have such a system of subsets of A that satisfy these conditions, then it is a partition of elements of A into subsets or into classes of equivalence. And with this system of classes of equivalence, we can easily formally define, introduce a relation of equivalence like that, just to belong to the same subset, to the same class. And it is quite obvious that they satisfy these relations, And inverse statement is also true. Each equivalence, sigma defined on set A, corresponds to some partition of the set A, to some system of classes. Okay, I believe we discussed it already, but I just wanted to remind you. Order relation and tolerance relation. Order relation and tolerance relation. A binary relation O, a binary relation O, is called a partition, a partial order. If it is reflexive, transitive, and antisymmetric. The partial order is often denoted, customarily denoted by this symbol, a greater or equal, greater or equal. Example, let P of U denote a system of subsets of the universal set U. Here, all subsets of the universal set, the system or set of all subsets. Then the relation of inclusion of subsets A sub I into A sub j. That, of course, is and these subsets, we can find them here. Here is a relation of partial order on P of U. Note, when we take a pair of A sub I, A sub j, they are subsets of U. Yes, of universal set. And at the same time, these two subsets are elements of this P power set of U. Elements of power set of U. Okay. Definition. A binary relation S is called a strict order, or many people call it irreflexive order or anti-reflexive order if it is anti-reflexive, anti-symmetric, and transitive. It is often denoted by this symbol greater, of relation greater. Now, here we have some additional concepts that are often used in discrete mathematics. Elements A and B, not only in discrete mathematics. Here we discuss tools that are used in many branches of science, many fields of science, including the statement of a problem for writing a program, for designing an algorithm and writing a program, and for other purposes. That's why elements A and B of some set are called comparable on the basis of the order relation R if either A, R, B, A is in relation R to B, or B is in relation R to A. If these statements, one of them, is true. Only one. Either this or this. A set A with the order relation, strict or partial, defined on it, is called completely ordered if any two elements of A are comparable on the basis of. Excuse me. Here, comparable. No. Here, if we speak to be comparable, if either A in relation R to B, or B in relation R to A, or both. Because if we can use instead of R, we say here strict or partial order. and with the partial order, then both cases can be, available. Examples. Numbers on the number axis are completely ordered on the basis of the relation more or less. By more or less, it is a strict order. The relation not heavier between the weights of different objects is an example of the partial order. Partial ordering. So we said partial order, strict order, and any of these order relations can be used for arranging elements and be in, because all of them are now comparable. If at least those elements that are comparable. Examples. I mentioned it. Definition. Binary relation T, capital, is called a tolerance on set A if it is reflexive, symmetric, and non-transitive. Here, I give you an example. I think we discussed. Let A be a set of all 4-letter arrangements. Arrangement, it is ordered sequence. An arrangement sequence, it is ordered sequence. 4-letter ordered sequence, it is sequences like this. A, comma, it is one 4-letter arrangement. B, it is another arrangement. And of course, A, B, A, it is another arrangement, and so on, because the sequence of elements is important for differentiated, to see the difference between such arrangements. A relation of tolerance is defined on the set of such arrangements. How do we define it? An arrangement X is tolerant to arrangement Y, for example, this and this, if Y differs from X only by not more than one symbol in corresponding position. Here, all of them are different. That's why only these are in this relation. We can take this is in relation to here, to this sequence, or this in relation to T here. Okay, because only in position number 4. Then the following sequence of 4-letter arrangements in this sequence of 4-letter arrangements. 4-letter arrangements. Of course, they belong to this set, each of them. Each 2 neighboring arrangements are linked by relation of tolerance. This is tolerant to this. This is, of course, this is tolerant to be tolerant, symmetric, reflexive, because not more. But here, yes, Mucha is tolerant to Mucha because not more elements, positions differ, 0 positions differ. Okay, tolerance. But this is tolerant here, but this, after that, this tolerance here, but after that we come to this element. Mucha is not tolerant to Tura. No, because 2 positions are different. Tolerance is a formal substitution for the intuitive idea of resemblance. Resemblance, похожесть. Similarity, likeness. Okay, I was a bit hasty to explain what is resemblance because I gave you some synonyms, and I'm sure that some of them is familiar to each of you. In the first object, if the first object is like some second object, and the second is like a third one, it does not mean that the first and the third objects are also similar. Like A knows B, B knows, for example, these are not just sequences, but people. A, B, C, D. A knows B, B knows C, but it doesn't mean that A knows C and A knows A, B, C. Yes, it does not. To know some problem. Okay, and I ask you, find some other example of tolerance relation and check the property of this relation, because they are not that frequently mentioned in the books. Okay, people, I reminded, maybe we discussed almost everything in the previous lecture, in some of the previous lectures, but I decided to remind you. Do you have any questions?
Да, есть. Как раз по последнему пункту.
Давайте. Go ahead.
Вот как понять, что она симметрична? Вот на примере там, где муха была, и что-то дальше.
Ага.
Да, ибо по циферкам это на матрице понятно. Вот
То есть рефлексивность и антитранзитивность ясна, а как вот с симметричностью быть?
Okay, but how do we define the relation? An arrangement X is tolerant to arrangement Y if it differs only by not more than one symbol. If I said that if it differs by one symbol only, then muha, it doesn't differ to itself, it doesn't differ from itself, and it is not in the relation that we defined here. But we said if Y, X differs to itself in not more in one position, but it doesn't differ at all. It differs in 0 positions. 0 is not more than 1. So 0 or 1 are allowed to have here. We put here only the sequences for letter arrangements that we are interested in, just to show you that how just we can lead you some, how to say, nasty, clever people, I don't know, clever or just tricky people, they can lead you to a wrong conclusion that actually here, if you don't see that the muha, do you see much difference between mura? No. So we can say, well, very similar. We make a step here. After that, mura, does it differ too much from tura? What was it? Just one letter? Shall we talk about it? Nothing to argue. Will mean them the same. And after that, come to Sloan, and after that, well, frankly speaking, I proved you completely logically that Well, there is no much difference between Mucha and slow, because you did not argue about the difference here, about the difference here, different, and after that come here. But we must state, if we state from the very beginning that here there is no transitivity, that you are just pretending that they are. Now, the difference is too drastic now to say that Torah somehow represents Mucha. So this is a method that some people use to make other people to consent to what they don't want to give, to agree, to what they don't want to agree. Well, okay, so we defined not more, Mucha, from Mucha, 0 positions. Mura from Mura, 0 positions. Any element here differs itself in 0 positions, which is not more positions. That's why, as we defined here, it is, as we define the relation here, it is reflexive. Did I answer your question, people?
Ну, по рефлексивности было и так понятно, просто вот с симметричностью.
Симметричность? Oh, very nice. Mucha differs from Mura in 1 position here. After that, Mura differs from Mucha in 1 position. That's why if Mucha is in the relation to Mura, then Mura is in the same relation to Mucha. It's quite clear, because they differ in 1 position. But
Понял, спасибо.
But now what is also clear, that yes, in relation, but here not in relation. That's it, not transitive. And everywhere the same thing. Because otherwise, we have to agree that if we have Mucha, it is the same. I can sell you as if it is an elephant, because it's the same. Okay. Now one minute left. People, any other questions? If no, let's have 5 minutes break and register if you did not. After that, I think I have not started to record. I will start. It doesn't matter. Thank you. Have a break, please. Okay, people, are you there?
Yeah.
Yes.
Yes, may I ask you, group number from 1 to 3, do you see this screen, lecture 4, functions?
Yes.
Yes. Okay. And oh, it's of course, it's not quite evident for me. And groups 0.5, do you see this screen, lecture 4, function?
Yes, we do.
Yeah.
Yes, great, great. Uh-huh. So we will briefly discuss now the next topic, functions. Functions, which is a special type of relations. A function is a special relation. Oh my God! Oh my God! Oh my God! Oh my God! Should I? Just a moment. With your permission, I'll start recording the lecture. Though they say it is not a must, but it is not. But they say it's preferable and so on. Uh-huh. Do you still see these lecture 4 functions or not?
Yes.
Great. Because any step might delete it from the conference. Definition. A function consists of 3 things. First, non-empty set A, called the domain of the function, the domain. Actually, okay, you will see what is it. A non-empty set B called the range of values of the function. The domain of values of the arguments, if you like, the domain of values of arguments. B, range of values of the function, domain range. And a rule that assigns to each element of A one and only one element of B. Okay. Notation. F colon A arrow B, read. F is a function from A to B. F is a function from A to B, from the domain to range. If A is an element of A capital, A small is an element of A capital, then F of A small is the image. So actually we are used to the name of the function, a value of the function for argument A. But well, in general terms, it is called the image of A under function F. Of A, of the argument A, under the function F. F of A, small, that belongs to B, capital, is assigned by A by the rule F. So these words are used very often to explain the situation when we just, consider real world objects and relations between them. And after that, if we find that the relation is a function, like a function, then we are happy and use these terms. Simple pictures. So This is a domain of possible values, 1, 2, 3, and they make the set A capital. This is the range of values of the function 10, 20, 30, B. This is the function, because every element from the domain has only one corresponding element from the range. 2 only 10, 3 only 30, nothing else. And if we have such a relation, because it is a relation between two sets A and B, also a relation is like this. 5 belong to the set which is supposed to be a domain, but it has two corresponding elements in the set which is supposed to be the range. Well, in this case, it is not a function, and it is not a domain of the function, and it is not the range of the function. Just an ordinary relation. Example, let A capital be a set of integer numbers, negative, minus infinity to 0, from 1 to plus infinity. And B, it is the set of just positive numbers, from 0 to infinity. We can define a function f from A to B by the formula f of x equal x squared. So the value of the, I wanted to say argument, the value from the domain and its corresponding element from the range is obtained by such a formula. Here we specify the rule f. Let S be any finite set and P of S be a power set, actually system of subsets of S. Then we can define a function f from P of S to N by the rule f of A, some subset of the, that is an element of this power set, is the number of elements in this set A. For each subset A of S, in plain words, f of A is the size of A, If we just define it like this, this is the rule, the size of A. General types of functions. Definition: function f from A to B is called surjective. If for every element B, small from set B, there is at least one element in A for which f of A from here is equal to B. So for every element, so in other words, if every element from the range is used or is linked to some element from A, then, and in a single way. So X only one element, B only one element 1, C only one element, D only one element. So it is a function. All elements here are used, That's why it is a surjective function. Surjective function. Well, here I just, if, for example, we have 1, 2, these are elements from B, and f of x here, 1, f of B, 1, f of C, 1, f of D, it is 2. That's why function is surjective. But another example, that set A includes such 4 elements, B, C, D, X. And set B, it is again 1, 2. Now, G of B, another function, not a G. G for this B is 1. The value of the function G for C is again 1. For D, it is again 1. And D of X, it is again 1. So we use only one element here, but not this one. That's why G is not surjective. There is no such element A here, from here, such that G of A is equal to 2. Definition. Function f from A to B is called injective. If for every 2 elements, A sub 1 and A sub 2, which are not equal, for every pair of elements, if they are not equal, then their images f of A is not equal to f of A1, f of A1 sub 1, not equal to f of sub 2. Example here. This is elements of A from the domain. This is domain. This is the range. And if 4 from the domain is not equal to 5, their images are also different. Here, different because 6 not equal to anything, 7 also different. Okay, such a function. So actually this function excludes the situation when 2 elements here have the same image. Here a function is injective. Well, here is another function of an injective. But on the other hand, the function G, this is Z, G from Z to N, number of natural numbers, set of natural numbers. Z, it is a set of all integer numbers, positive and negative, and here set of positive numbers. And the rule is we take element I from the domain, and by this rule find the corresponding element in the range. But here we had a situation -2 not equal to 2, but G of -2 is equal to G of 2, and it is 4. So this function is not injective. Now we come to a most desirable case in many cases in discrete mathematics and in other branches also of science. Definition. Function f from A capital to B capital is called bijective or bijective, but bijective. Bijective. If it is both injective and surjective, both injective and surjective, it is a one-to-one correspondence between the elements of A and the elements of B. So if we have such a function that is injective and surjective, and then one-to-one correspondence. A symbol of such a function, set of values in the domain, symbols, 256 symbols of ASCII codes. ASCII codes. No. Symbols that are used in preparing text files, suppose text files. And here, ASCII codes of their symbols. Every symbol here has its own ASCII code. ASCII code, what is it, ASCII code? It is 1 byte, 8 binary positions. 8 binary positions. That's why 2 to the power 8, it is 256 possible codes. And hence, this table of symbols and their ASCII codes should contain 256 symbols. And there is exactly one code to each symbol. And each symbol has one code. And here I showed you on purpose. A capital has the code 65, not minus. Well, I don't know why I put here. I just, my God. It is not minus. I just wanted to show that, well, a link, but it looks as if minus. No, everything's possible, positive. 65, B. Of course, one more, 66, B capital. A small, 97. B small, 98. 98. Oh my God. And here we have a function. Set of 256 symbols and into the set of numbers from 0 to 255. And I just say C small. ASCII code of C small is 76, 67. Well, look here, A. Oh my, oh my, oh my. Stupid. It is an error. C capital. Oh. F of C, A, B, C capital, 67. And F of D, A, B, C small, 99. D small, it's code 100. So like that, etc. That's why I just put those values for you just to remember them. A capital, ASCII code 65, and A small 97. And after that, you can get any ASCII code for the Latin letters, or English letters or Latin letters. If you remember the English alphabet, if you A, B, C, D, E, F, G, H, and so on, until Z. If you remember, you can easily just obtain the ASCII code, which is an important thing to know when you are programming in some languages. like C++ and so on. In Java, you use Unicode. There we have 200, 2 bytes and more codes and more positions. But basically here maybe the same. Okay, the first. Okay. It is an example of a function given A, 65 capital. Given 65, you get A capital. A 1-to-1 correspondence, a function which is a 1-to-1 correspondence. While composition or product of functions, which is quite similar to product of relations. Definition. Given 2 functions, f from A to B and g from B to C. The composition of functions f and g is a function from A to C, from A to C, that is defined, that is denoted and defined so, denoted and defined so. G product f, it is name of the function. Again, same column, from A to C, where G product f function of A, it is same as G of function f of A for all elements from A, for all elements from A. So it is like you can visualize it using such a picture. Set of range domain for function f. This is range for f. Now this set becomes domain for G, and here range for the product of functions, and also for G. Okay, let A consists of 3 elements, A, B, C. B, 4 elements, consists of, includes 4 elements, 1, 2, 3, 4. C, now it includes such a strange set, A, 2, minus 6. So characters, but well, we can consider character as a ASCII code, then it becomes a number also. Let f of A be defined by pairs. F of A 2, it is in B, 2, f of B 2, f of C 1. So we use only these 2, 1 and 2 elements from here. And we actually mentioned only A, B, C from here, all elements. After that, G from B to C be defined as G from 1 here, G of 1 is equal to A. G of 2 from here equal to minus 6. G of 3 here equal to minus 6. G of 4 equal to A here. Then the product of function G of f from A to C is the function defined by such pairs, not such lines. Gf of A is G of f of A. It is G of f of A, it is 2. F of A, it is 2. G of 2, it is minus 6 here. After that, we do exactly the same thing. G of 2 minus 6, G of C, G of FC, G of 1, it is A. It is like that. It is like that. We used now only some values from here. A to 6, A minus 6. 2 wasn't used in this product. And here, one more example. One more example. Well, it looks somewhat, how to say, complicated at the first glance, but it is very simple. Let S be a finite set, some finite set. What elements we don't care. And X be an element not in S, not in S. Function F, one function, is defined so from subsets, a universe power set from power set of S. Here we have all possible subsets of S to the power set of an extended set, where this S is added one element X, one element X. So now here we have not this S. Before here we used element without X. Now we have all subsets with X in it. And what is the rule? Which we take some subset here and put into correspondent another subset here. The rule or function is defined so: f of t, it is some subset of S. The result or the value of the function is the same t united with X, for all t subsets t in this union set. After that, G, we are driving at an example of a product of the function. That's why we discussed that here we have a function that adds one more element to each subset from the power set here, just include it. And here another G. And this takes the elements, subsets from this extended set, and the values numbers be a function defined as so. G of V, it is some set, and the value of the function is number of elements in this V. For all V in this power set, for all subsets here. In such a case, the composition G product F from PS to N is given by T product F of some set T. What is it? T, it is subset here. From subset of S is equal g of f of t. F of t creates, take this t plus x, not plus, union x. So it is g t union x equal to the number of elements in this extended subset, which is equal to number of elements here, of course, plus 1 for role t in PS. So, well, somewhat, well, lengthy, but described quite clearly, formally, without any ambiguity. So this is how they define necessary relations and functions in, if necessary, in discrete mathematics, programming, and programming also, and programming. When we define the some formula, some function to be programmed. Okay, people, here I just introduced you to this topic in order for you to learn the very important terms, concepts, to understand quite clearly what is it a one-to-one correspondence, which will be used not once for proving some theorems and so on, and also to understand what do we mean by product of functions. Okay, do you have any questions, please?
Да, есть один вопрос, вот как раз по последнему пункту, который мы обсуждали.
Да.
Я не совсем понимаю, ну, все доказательство предельно ясно, но непонятно, зачем оно. То есть, если мы в каждый элемент суперсета добавим еще один элемент, то как бы количество в каждом подсете будет на один больше.
Зачем это?
Да.
А зачем это? Зачем мы можем хотеть иметь такую функцию? Да? Вот это вопрос.
Да, да.
О мой бог. А зачем мы можем хотеть такую функцию, такую суперпозицию функций? Да
Ну,
просто для примера. Для примера. Чтобы вы поняли, что такое, ну, не суперпозиция, а композиция функций. А здесь мы уже вроде бы все, так сказать, уже уяснили для себя, что такое power set неоднократно, что такое union of sets неоднократно. А теперь вот взять вот эти вот чисто математические, так сказать, символы и так далее, ну, уясните, а что же имеется в виду здесь?
Просто
для примера. Это вовсе не для того, чтобы строить здание или что-нибудь. Ну,
то есть мы и так понятный факт просто описали математически, что если добавить один элемент, мы пришли к тому, что там будет вот количество в t будет плюс 1.
Да, если хотите, да. Если хотите, да. Но очень зачастую наука требует использования, каждая наука требует использования своих терминов, чтобы, ну, не ну, как вам сказать, чтобы что? Чтобы дать свое осветление объекта исследования. Вот так.
То есть мы на практике доказали то, что сказали на словах, правильно?
Нет, но мы... Нет, почему доказали? Мы просто... Здесь ничего доказательства нет. Здесь ничего доказательства... Здесь просто дали окончательное пояснение. Вот здесь вот. Раз, вот это определили. А потом окончательное пояснение. Что же мы имели в виду? Потому что вполне возможно, что мы вот это вот сейчас G мы могли вот здесь вот бросить вот на этом месте, а это уже и не рассматривать. Вот. Сказано достаточно. Я чуть-чуть добавил сюда, чтобы было понятно, а что же было сказано. Потому что G-то мы уже здесь вот уже это определили, вот. И теперь сказали, а вот наша суперпозиция.
Все, то есть это
Так,
как пример
и
был.
все. А это как бы некоторое пояснение тому, что это вообще этот символ означает. Даже вот здесь можно было бросить. Вот. Вот здесь.
Да, понял. Спасибо.
И вот здесь даже. Потому что дальше это уже все, так сказать, поясняет, как ее высчитывать, А сказано вполне формально и точно здесь. А дальше вот это маленькое пояснение тому, что здесь. Потому что, да, можно было с самого начала взять и сказать, что вот наша функция это вот это. Раз и все. И не упоминать. Но если у нас уже есть две хорошие функции f и g, для каких-то других целей объяснена, теперь мы можем ввести новую функцию для, так сказать, для использования. Ну, чтобы не определять еще новую отдельную функцию. А f, g, h, функцию h, которая вот так. А зачем? У нас уже есть f и g. И вот в этих терминах мы вполне можем уже многое объяснить. Ну, вот такие дела. Anything else? А что это? Еще 7 минут. Хорошо. Ребята, я сейчас не задаю никаких вопросов вам по поводу лабораторных работ и прочее, если вопросы за пределами вот этой лекции. С тем, чтобы обсудить это подробнее на консультации. А вот сейчас я Сейчас.
Не, он работает.
Нет, это я просто включаю. Вам сейчас propositional logic. Вам сейчас, конечно, не видно. Lecture 7. Propositional logic. Нет. Потому что теперь каждый раз, прежде чем... Окно. Теперь. Just a moment. Окно. Скажите, люди из первой, второй, третьей группы, вы видите вот это Lecture 7, Propositional Logic?
Да.
Отлично. А четвертый, пятый вы видите?
Да, видим.
Да, видим.
Так, ну вот, у нас есть целых 5 минут. Немножко поговорим, так, потому что, к сожалению, мне пришлось прервать логическое следование вот этих лекций. Ну и, может, мы потеряли время. Lecture 7. Propositional logic. Propositional logic. Originally, the two-value Boolean logic was developed by George Boole. England, he lived in England from 1815 to 1864. It was developed by this George Boole to explore which natural language statements are logically sound, ну, правильный, корректный, sound. Но sound это еще и здоровый. Ну, здоровый голос и нездоровый голос. And which are not. For some decades, this mathematical tool had no practical application. Later, it was found that two-value Boolean logic is very convenient for performance description of electrical circuits with switches, computer electronic circuits, and other devices, systems, and equipment. Definition. A statement is any sentence that can be true or false. That has a truth value, in other words. Example. A statement. Kharkov is a city. True. Now it is summer. False. Some birds can fly. True. These are examples of statements. Or propositions. Statements or propositions. These are. Other sentences. Go home. This is an order. What is your name? This is a question. It is not these are not statements, not propositions. Okay, so what I'm saying is not true. Another sentence. So these are not statements because orders, questions, but here, what I'm saying is not true. It looks like a narrative sentence which must be true or false. I tell about something, but if it corresponds to a real situation, real life situation or not, we just have to decide. But we cannot say if it is false, then what I'm saying must be true. We say false, at the same, it must be true. We say true, then it must be false. So, controversial. The barber shaves everybody who do not shave themselves. Okay, these are paradoxical. The same thing. What he does to himself, does he shave himself or not? If he shaves himself, then what is the meaning here is false. If he doesn't shave himself, then he must shave himself. So we cannot decide if it is true or false. These are paradoxical statements. They have hidden contradiction. It is impossible to say if they are true or false. Okay, people, if you don't mind, we'll stop now. I just invite you to read a bit at home. See if you like it or not. And after that, later will come, hopefully, to understanding what is the use of all this simple theory. Simple at the superficial glance. It is far from being simple when it comes to real applications. Okay. Any questions, people?
No.
No. Thank you.
No question.
Hopefully.
Thank you.
I will see you at the consultation.